Okay. Okay, most of you already know what what recursion is. A function calling itself. Yeah, that's an acceptable answer. I cannot say no to that. But what really it is, I will just let's dig a little deeper. Let's dive little deeper into it. With right now we have a little example here. We have main function and we have a fact function. Yeah, it's a factorial program, simple one. If you look into factorial function, fact function, you can see it is calling itself here on line number 8. Okay, now we can say this is recursion because fact is calling itself. Okay, if you notice on line number 7, we also have one more statement here. A recursion has a base statement. Yeah, that's the base statement. We want, recursion to stop at that point. When I equal to 0, we want to stop the recursion. We want to return 1 and stop the recursion. If we have no, base case, the functions will be calling itself, and we would eventually get an stack overflow error. Okay, that's a recursion for, loops. Let's run this. Okay, it's working as expected. Factorial of 5 is 120. But let's just visualize it. Okay, guys, recursion is best represented in trees. As you can see here, we have one big tree. Okay, we have a function here, factorial. It's just written in Python, doesn't matter. And we are calling factorial of 5. So when we run it, see, that is how our function calls are called, and we'll look into it one by one. So first we are initially calling factorial of 5. So what factorial of 5 does is it calls factorial of 4. As you can see here, initially fact 5 is called, and then we are calling factorial of 4. I minus 1. 5 minus 1 is 4. So what factorial of 4 does is it simply calls fact of 3, and 3 does is 2, and then 1. And when it reaches 0, we have the condition base case, right? A recursive function always has a base case. It can be single or more base cases. If you look at it, we reached 0, so it returns 1. So when we reached 0, it returns 1, and 1 goes here, the last one here. So 1 into 1, which is 1. So this recursive call returns 1. See, it returns 1. And 1 into 2 is 2. That recursive call returns 2. And so on. 3 into 2, 6. 6 into 24, 24, 5, 120. That's how recursive calls are made internally. These all are functions, guys. Function calls. There's 5, 4, 3, and a stack. A stack is used basically for function calls. So when we want to use, when we have to use this recursion. So if you look at factorial example, what is factorial of 5? Well, it's 5 into 4 into 3 into 2 into 1. We know that. But factorial of 5 can also be represented as 5 into 4 factorial. 5 into 4 factorial. And factorial of 4 can be written as 4 into 3 factorial. If you notice here, we have sub-problems in our problem. Finding factorial is a problem. And then we have sub-problems in it. As you can see, if we know 4 factorial, we can find 5 factorial. We just multiply 5 with 4. We get 5 factorial. When a problem has sub-problems, we can just use recursion. And recursion is costly if we have any iterative approach. If we have any iterative solution, then we must proceed with iterative solution, as iterative solution is much faster than recursion. Why recursion is slower? When why it is slow means, internally, see, it has to call 4, it has to call 3, 1 and 0. It has to make 5 other different calls, which is costly. So prefer iterative over recursion. Okay guys, but when it comes to backtracking, then what is backtracking? Well, backtracking is you know a technique widely used in recursive algorithms. Let's go with an example here. If you take a look at here, we have doors. We have 4 eights. Okay, we have 32 doors here. So my question is, out of all these doors, uh, 3 doors, behind 3 doors, there is gold. There is something valuable. So I ask you to, find out where the goal lies. One would simply, one would simply go one by one door after the other. He would start here, then go here, then go, then. Eventually, if he finds gold at number door 4, no, at number door 4, he'll come out. But there are 2 more doors, which has, there behind 2 more doors, there is gold. So what he'll do? One would, simply not walk away. He would come back. He would come back and visit all the other doors too. If he did not find any gold in the first door, he'll go to second. What he's doing exactly here? He's coming back and visiting the second door. That's basically backtracking in general. So basically in backtracking, we attempt to solve a sub problem, and if we don't reach the desired solution, desired, here we want to find the gold. We want to find 3 pots of gold, not just single. Okay. uh, so basically a backtracking, we attempt to solve a sub problem, and if we don't reach the sub solutions, that sub desired solution, then we undo whatever we did for solving that sub problem and try solving another sub problem. Just like I told you before, initially we'll step into door number 1. If we did not find any gold there, we come back. We are undoing the step and visiting the door number 2. That's basically a backtracking means, guys. I hope I'm clear. Okay, let's see a problem first. Okay. So the problem is, generate all possible subsets of set. The question here is, generate all possible subsets of a set. So all possible subset, it's nothing but a power set. So we want to find all the possible subsets. So here is the starter code. We are not doing much here. We have nums, a vector of nums, and we have the length of it. And this is doing not much. Let me remove it. And we have a function, find subsets, and we have to find the solution for it. Let's visualize it first. Okay, if you look here, we have an array 1, 2, 3. It's a vector. So what's the idea behind this is we start with a subset, null set. First one here is empty set. And what we do is we don't include any item. I is initially at 0, which means I is basically the index position of array. So we start here. So I is initially 0. So what we basically do here is we don't want to include whatever it is at I equal to 0, and we want to include whatever it is at I equal to 0. So array of I0 is nothing but 1. So we don't want to include 1, and we want to include 1 on the right side. And on the right side of the tree, we want to include 1. If we go a step further, at I equal to, we increment the I as we go deeper. We don't want to include 2 when I equal to 1, the value is 2. We don't want to include 2. We want to include 2. Are you getting this? And if we go one more step level deeper, at I equal to 2, we don't want to include anything, which is 3. So we get a null set here. A null set is a part of power set. So it's basically a subset of a set. And we want to include 3. We basically do this for every set, for every element in the array. So all the bottom part here of the tree are the subsets of all the possible subsets of the set 1, 2, 3. If you look, and guys, the possible subsets of a set is nothing but 2 to the power of n. So here n is 3, 2 to the power of 3 is 8, 1, 2, 3, 4, 5, 6, 7, 8. We do have 8 values here, 8 sets here, null set and the others. So the basic idea behind generating all the possible subsets of a set is this. We want to include, we don't want to include. Okay, let's, okay. So what is the first step? Can anyone tell me what is the first step in a recursion, in a recursive function? You can type it in the chat box. What is the first step when writing a recursive function? We already discussed. Okay. The first step when we are writing a recursion function is finding out the base cases. When we want to stop the recursion, that's the important step, important and initial step. So if we take a look at here, when I equal to 2, we don't want the recursion to move further. We want to stop at I equal to 2. So what is I equal to 2? It is nothing but length of array. 1, 2, 3, basically it's nothing but length of the array. So what we do here is initially we pass I equal to 0 if I equal to the length of array and start size. What do we want to do here? We want to, when we come here, we get the subsets, and we want to store these subsets for printing them later in some variable. So I'll choose, we already have subsets. So I'll push my subsets in here. So when we are at this point, we have one distinctive subset of all possible subsets of a set. So we are pushing that subset into our all subsets global variable. So here we want to stop the recursion. We don't want to proceed further. So what is a recursive case? Well, if you look at here, as I told earlier, we want to include some element and we don't want to include some element. So I want to, first, I don't want to include anything. I plus 1, we are going a level deeper. So we are basically calling it as it is with I incremented. So we are not including anything here, which is nothing but going to the left side of the tree. And we want to include the first element, which is 1 here, that element in the next call. So what we do is subsets.push. I want to include that thing. So I'm pushing the first element, which is 1 initially, and then I'm going to call the next recursive form, recursive call. Okay, guys, we made these 2 steps here. We don't want to include anything, and we want to include something in it. Okay. And guys, we also need to add another step here, subsets dot pop. Okay, why am I adding this line 15? Assume you're here 2, 3. You went all the way down to 2, 3. When you go back, we don't want 2, 3 here. We want whatever previous value we have, which is 2. And when you go back, we don't want 2, we want an empty null set. Guys, when you look at the code here, first all the left part of the tree is called. See, we don't want to include anything. Is the first recursive call. So all this left part of subtree is executed first. So we don't want to execute anything here. So when we are trying to execute this part, which means this thing, we don't want anything in that thing. We don't want any subset here. So when we have 2, 3 here, we are backtracking to here, the previous recursive call, and we are removing 3 from here. This is what I did here. So I'm calling the step. This step leads me to 2, 3. Assume that. So this steps removes the whatever we added. We added 3 in our previous case. So I want to remove 3. So I'll just pop it back. As I said earlier, backtracking, if we don't find the solution, or if we want to find another solution, then we undo whatever previous step we did and try it out with another sub solution. So we pop it back. Yes, this is what backtracking is actually. So that's it, I guess. This code should do fine. Okay, let me print all the subsets. Guys, auto keyword here is it takes whatever value it has. If I is a string, then auto is a string. If I is a number, then it's a number. So I want to print J and a little space after it and a new line. This should give us all possible subsets of a set. Let me run it. Okay, we do have the output. How many are these? Okay, let me print the size of the all subsets too. If you take a look at here, we have 32 possible subsets of this set 1, 2, 3, 4, 5. And I already told you before, all the possible subsets of a set are nothing but 2 to the power of n. So here n is 5, 2 to the power of 5 is 32. And we also have all our subsets, possible subset. Yeah, that's it. That's it for generating all possible subsets of a set. If you have any doubts, you can ask me, or you can type it out in the chat box. Okay, I hope you don't have any doubts. I'll move on to the next problem. Okay, our next problem is generate all permutations of a string or an array. Anything will do. Okay, generate all permutations. First of all, what is permutation? Well, simply it can be rearrangements of order rearrangements of things. If you have 1, 2, 3, if we rearrange some values 2, 3, 1, this is a permutation. Okay, how do we solve this program? We want to rearrange all the possible values here. Okay, first of all the possible permutations of this string 1, 2, 3 is nothing but n factorial, which we have learned in our school. So 3 factorial is nothing but 6. We should be able to. Okay, how do we do this? Okay, let's jump into the picture. Okay, we have ABC here. So the basic idea behind this problem is we want to fix one value aside. We want to keep one value aside and then play with the other two. Okay. If you look at here, ABC, this is the first initial call. And we are swapping A with A, which means we want to keep aside the A. Okay, we arranged A. Again, we want to deal with B and C. We don't want to deal with A because it is already rearranged. Again, we are fixing B here initially, and we want to play with A and C since B is fixed. Similarly here, C is fixed, and B and A, we want to swap them, or we want to do extra modifications to them. So what is exactly happening here? We are swapping the first value with every other value. Then we get these three. If we swap A with every other, not other, with every value in this array, ABC. So we get ABC, BAC, CBA. Okay. And then now that A is fixed here, B is fixed. You cannot move A around, you cannot move A to C and C to A, because that's just gonna result in duplicate elements. So we want A to be fixed, and we want B to be fixed, C to be fixed. The red values here, B, C, A, C, B, A, we want to swap those, rearrange those values. So same thing we did here in the previous recursive call. We have to do it here. We want to, swap swap B with with every value of that array, which is BC. Guys, A is fixed here. We don't want to touch it. If we touch it, we will, the answer will be resulted in duplicate elements, duplicate permutations is what I meant. So what we are doing is swapping B with all the elements in that BC array. Okay, we are swapping B with B and then B with C. We'll get ABC, ACB. Similarly, in other recursive calls, we'll get all the possible permutations. When n equal to 3, which is n is the size of the array, number of possible permutations are n factorial, right? So we have 1, 2, 3, 4, 5, 6, 3 factorial, which is 6. So this is the idea behind the problem, guys. So okay, let's try to solve it. The first thing in writing a recursive function is, as I told earlier, it's the base case. Base case matters. If you don't write the base case well, it's gone. Recursive function is gone. So the base case here is what we want. When the element in array is a single character, we don't want to repeat further. So we have ABC here. When there is only one character left over in the vector or array, then we want to stop there. If you look at here, ABC, here C is left over and C is single character, and we want to stop it here, because if you swap C with C, you're going to get the same thing. There's no other element to swap it. Similarly here, every other place. So we got the base case, which is if, okay, let me first tell you the starter code. We have the string here, 1, 2, 3, and then we have generate permutations is a function, recursive function. We have to write it. We are passing a string, and this is nothing but index I equal to I. Initially it's 0, and then we have string length, which is n. So if I equal to, we want to stop when there is only one character left. When that happens, when I equal to n minus 1. In this case, there will be one character left. So that is where we want to stop. So let's print here. If we, okay, let's print str here. Okay, what str here is, if you look here, ABC, that's our str value, string value, ACB. Okay, so what we have to do here, we want to swap every element with whatever element we have at I equal to 0. index I equal to 0 of the str. So since we want to swap every element, we need to use for loop, and we want to start at I. Initially I is 0, so initially we will be iterating from every element from string in string. So we want to stop it, and okay, what we have to do here is we need to swap. Here we are swapping A with A with B, and A with C, swapping every element with the other element. So I want to swap, not this one. So I want to swap str of I, which is the first value. Here it's 1. Okay, let me take this as ABC. Then there will be no confusion. Okay, so initial is str of I is A. Since I equal to 0, I want to swap it with itself, the element which is at str of J. Initially J equal to also 0, so it is swapping with itself basically. Again, after, okay, I swapped the first. Okay, now I'm able to swap every element, every first element with the other element. I mean, A. Now with this for loop, we should be able to swap A with A and B and C. So we are here. This step is completed. We should be able to, first half of the tree. We should be able to see first half of the tree. And we do want to swap. We do want to go a little deeper into the tree. We want to call the generate all the permutations. And then okay, we call the generate all permutations, and then we want to swap back. I mean, if you look at here, click here, we have ABC, ACB. Suppose you are here, the function is executing this part. So when you go back, I want BC. I want BC in our untouched array. I want A to be fixed, and I want B and C to be there. So I want to undo whatever swap we are doing here in the backtracking step. Okay, and then backtrack again here. So we want to undo whatever step we did to go to that step. This is a step we did, so we want to undo that. J. This should work. Okay, let me check. Okay, yeah, we got the output, guys. 1, 2, 3, 4, 5, 6, A, B, C, A, C, B, and others. Yeah, it matches the output here. We should be able to do this for vectors. It doesn't matter which data type we have. So that's it, guys, for generating all the permutations of a string. So what we have learned so far is recursion. Recursion is nothing but a function calling itself. So generate permutations is calling itself inside its body. So we call this recursion. Every recursive function has at least a single base case. So here is our base case. Okay, here we are not stopping. Yeah, it works. Like, I don't have. Yeah, okay. Mm. So every a recursion is nothing but function calling itself, and every recursive function has a base case. So here we have this, and then here we have this. So let me show you what actually happens if we have no base case. I don't know how this ran. So fact. So let me call itself fact with incremented value. And I don't want to have a base case here. Let's just, output it. Okay, let's see what happens. Yeah. As you can see, the I is getting incremented, and we reach some value, which is in some 2,61,000 value. And then we got the error. This is basically a stack overflow error. Yeah. So this is what happens if you have no base case in it, because you call. This number might vary depending upon the operating system and also on the language you're using. Here we are using CPP, but in Python, you know, there can be more there can be more space available, so there can be more high values here. So yeah, that's it, guys. This has been recursion and backtracking. Okay, in the next week, we'll be seeing part two of recursion and backtracking. There we'll discuss some other problems. Well, until then, bye.